Hello all and welcome to this first module of Optical Communications MOOC course. In this module I will give you a brief overview of optical fiber communications. The idea is not to be very comprehensive. If you do not understand one or two topics here, or if you do not understand most of the topics here, do not worry, the entire course is for this expanding upon what we are going to cover today. We will be revisiting all the topics that we discuss in a very brief manner. The idea of this overview is to tell you what is optical communications capable of doing and how it performs this function, that it is very well known for that, and we will also discuss the course plan, suggested textbook and references, and we will begin with considering the overview of optical fiber communications. My name is Pradeep Kumar K and I am from Department of Electrical Engineering, IIT Kanpur. My email ID is given here on the screen. So, feel free to contact me once the course starts. We can talk about the questions that you will have. So, the outline here for the overview is that we will first motivate the requirement for optical fiber communications, and then we talk about the point to point optical communication link. I will talk specifically about modulation and transmission, also introduce you to receivers. Finally, I will discuss optical fibers. Remember, all these topics are going to be covered in the entire detail for the rest of the course. The idea here is to familiarize you with what is optical fiber communications and how is it currently deployed and what are the elements that go into making an optical fiber communication system. Now, before we get into optical fiber communications, here is a slide which I want to show you. This slide was taken from Cisco Global IP Traffic Forecast, which was couple of years ago it was published, and it makes very interesting reading here. You can see that the data traffic or the global IP traffic keeps on increasing from the values around 60 exabytes per month to the projected 170 or 168 exabytes per month by the year 2019. We are already in the year 2016 and the exabytes per month of the global IP traffic is already touching 100 exabytes per month. Now, this is just the IP traffic. If you look at the global traffic, the global data rates are expected to exceed 2 zettabytes per month by the year 2019. In another 3 years, we are expected to reach more than 2 zettabytes per month. To put this number zettabyte into context, 1 zettabyte allows you to store 1 trillion movies, each movie assuming at 1 gigabytes. That is a non-HD format. Most movies are available with 1 gigabyte of the size, and you can store 1 trillion movies. This is the entire movie in all of the different movie industries in the world. Put together, this number would not be exceeded. So, you see that by year 2019, this is the kind of data traffic that is expected to be there for the entire world, and this traffic implies that the world must be connected with very high speed data network. If you look closely at what applications drive this IP traffic, you will see that much of the application is by the internet video, something that you would appreciate it, including this online lecture that you are viewing currently comes into the category of internet video, and you can see that there is about 40% or 45% of the entire traffic is expected to be that, but by the year 2019 this number is expected to go up to 64%. So, we expect that internet video is already dominating, it will become even more dominating as the years go by. The next application that is consuming lot of data is IP video on demand. Then there are web data and file sharing, with which you can share files to your friends, you can share some documents that comes up, and finally there is gaming, which does not really see much of a improvement out there. So, these applications all consume enormous amount of data, and these applications are also sensitive to delay. You do not want to view a video in which one frame of the video comes now and the next frame of the video comes 1 or 2 seconds later. That kind of a delay is unacceptable. So, once the streaming starts, you want the entire video to be delivered to you or streamed to you. Unfortunately, this video traffic is not always upstream, that is, this video traffic is almost always consumed by the consumers rather than consumers putting out videos and putting on the connection from the other end. However, we also expect such certain novel applications to come up, such as video calling and peer-to-peer services. They are expected to make traffic symmetric so that the load on the network distributes evenly between consumers as well as the data centers. If you look at the context of India, internet in India is one of the rapidly expanding resource, and it is very clear why that is so, because now more and more people are getting connected through internet by either private networks or through public sector networks which are governed by the government of India, and this internet traffic is expected to go even more higher because of such initiatives by the government, such as online courses, which are again expected to increase rapidly. In addition to that, consumer data traffic also drives the internet traffic in India, and India is one of the fastest growing countries in terms of internet traffic. We expect that IP traffic, or when I say we, actually I mean the Cisco Networks expects that the IP traffic in India will exceed 2 exabytes per month by the year 2017. Okay. Now we ask, well, we are seeing lot of data being communicated. Now what actually does it take to communicate? What infrastructure is required for me to communicate at such high data rates and possibly with very low delay? That is, the network or the infrastructure must be fast enough in order to perform all these functions to transfer the data. It must also cause no delay. Okay. Well, two characteristics of communication come up very naturally. One is that you are looking at long distance communications. Why are we looking at long distance communications? Remember, your data center may be located in the United States and you might be sitting in India and accessing some data from the data center, which means that you are on two different continents and you are now connected through a infrastructure, communication infrastructure. It is of course not only two users, there are millions and billions of users who are connected via internet, and this internet spans continents, right. In order to have long distance communication, you also want the communication channel to have very low loss. What happens if the communication channel has a high loss? Then whatever data that you are transmitting in a certain form, that will be lost before it reaches the destination, and we are talking about thousands of kilometers of transmission of data from one point to another point. Therefore, in order to sustain this long distance communication, the communication channel that you use in the network infrastructure must have low loss. Well, there was a very interesting idea that someone suggested to me as to why should you have a communication channel at all. What if possible that you take all the DVDs, whatever data that you want to communicate, put all the DVDs and post it or courier them to the destination. Well, it can be done. The data rate will be certainly very high. You can imagine, a truckload of DVDs being delivered to you, and the data in each DVD would be around 4 or 5 GB, let's say. So that entire data is available to you at the instant, right, when it is delivered to you. However, this transporting DVDs from one point to another point when you are far away across the continents will involve significant delay. So you cannot have 10 frames of CD of a movie arriving to you by post today and the remaining 20 frames arriving in the next post. So there is a significant delay in this idea. So that brings up to another aspect of communication. We want communication at long distances, continental connections. However, we want this communication to happen rather fast. We do not want significant delay in this communication. Also, because it is supposed to carry a large data rate, the communication channel must have a large bandwidth, right. So, large bandwidth, less delay are two other characteristics of long distance communications that you would like to have. The traditional communications which were happening over copper cables, I do not think you would find copper cables anymore, and for a very good reason is because data rates cannot be supported in the range of gigabits per second, and when we say gigabits per second, this is on the low ball that we are looking at, low ballpark that we are looking at. The data rate typically that current communication infrastructure supports is around tens of gigabits per second. So, it is clear that copper cables or any other solution, you can think of satellite, you can think of any acoustic wave kind of communication, none of those communication technologies are able to support data rates in gigabits per second. The third and one of the recent characteristic of communication that has now come to all of us is that users also want the data on go. That is, I have a smartphone, you have a smartphone, and you want to watch video not sitting at a home or turning on your PC or connecting to the television via internet. What you would like to have is that you are walking or you are running and you want to also watch video, or you are traveling from one point to another point and you want to watch video that is streamed to your smartphone. This is what we call as data on the go. However, for this to happen, the infrastructure must support mobile communications, and this mobile communication, which is implemented in the form of wireless technology today, still requires a high speed wired backbone network in order to give you mobile communications as well. So, this backbone network connects to stations and towers that are used in the wireless communication systems. Now, if you ask what technology addresses all these issues, there is only one technology which is currently making all these communications that I talked about with all the nice attractive features of long distance, low loss, high data rate, low or a less delay is made possible by fiber optic communications. And fiber optic communications today can support data rates in excess of 1 terabits per second super channels. Well, these are lab demonstrations, they have not yet been operational in the actual world, but data rates of 40 Gbps are currently available. So, much of the new networks that private network operators are setting up are running at 10 or its next cousin at 40 Gbps. So, there is already 40 Gbps available, and if you look at the aggregate data rates are in excess of terabits per second. Now, this is very important, the aggregate data is in terabits per second. Okay. 1 terabit is 1000 times billion. So, you can imagine the kind of data rate that is possible with current optical communication technology. No other communication technology such as satellite, wireless, copper cables, whatever communication technology that you can think of can provide such high data rate at such low losses. Okay. Now, how was optical fiber communications made possible? Well, optical communications has been in existence since around 1970, and two discoveries which were made simultaneously, these two seminal discoveries made optical fiber communications possible. The first one was the fabrication of glass optical waveguides, or what are now known as optical fibers, which allowed us to reach the so called magic number of 20 dB per kilometer, and this work was performed by a certain group of people at Carnegie laboratories, where they fabricated a silica glass with attenuation less than 20 dB per kilometer. Now, this magic number of 20 dB per kilometer comes from the older technology, where the copper cables had this kind of loss. The copper cables that were used for communication, for telephony and other things, they had this loss of 20 dB per kilometer. Therefore, there was a rush to try and get to that magic number of 20 dB per kilometer with optical fibers. So, if the fiber could deliver attenuations of less than this number, then copper cables could be replaced, because silica is cheap, it is abundantly available, glasses can be made with very little loss. Now, that is another interesting point as to how these losses were reduced, and losses were initially very high. Losses were at 1000 dB per kilometer when this concept of optical fibers were proposed, and then the loss steadily decreased, and now it was in the 1970 it was around 20 dB per kilometer. From there, the loss has been reduced to the theoretical limit of around 0.15 dB per kilometer. Today, losses are around 0.15 dB per kilometer. Therefore, you can kind of forget about loss as a major impairment in optical communication systems. Loss is almost not an important issue today. The other thing that made possible optical communications was the fabrication of a room temperature laser. Now, lasers, if you think about a laser, the first thing that would come to your mind is this huge helium neon lasers or ruby lasers or kind of different carbon dioxide lasers. These lasers all work at different wavelengths, they all emit light at different wavelengths, but one of the characteristics that comes to our mind when we say laser is that these are very bulky, they occupy a large area, and they have to be cooled always. So, if you look at a carbon dioxide laser, there is a cooling liquid such as water that is flowing around. So, in order to cool the lasing medium. So, this kind of operation meant that you could not really use this laser in conjunction with the optical fiber, and that is where semiconductor lasers were fabricated. These are known as double heterostructure Fabry-Perot cavity lasers, and these lasers had this attractive feature that you can control the lasing power by simply varying the current to the laser. Okay. And this came in a very small form factor, and most importantly this did not require an external cooling mechanism, and they were able to work at room temperature. Okay. So, they did not require this huge cooling stuff, but they were able to work at room temperature, and these two together. So, now you have a laser which is an optical source, and you have a optical fiber which is the guiding mechanism. So, you can take light from the laser, modulate it so that you can put the information on the optical source, and then couple that one to the guiding medium. There at the receiver end you put up a photodiode, which is again a semiconductor device which can again be fabricated on a chip, and then the corresponding circuitry can be arranged on a chip as well, and then you have your full optical communication link. So, you have the source in the form of a laser, you have an optical fiber which is the guiding mechanism, and then at the end you have a photodiode or a photo detector. So, optical fiber communications, as I said, was not possible without having these room temperature lasers and the development of low loss optical fibers. The concept of optical fibers was not really new, or in fact the concept of optical communications was not really new. Long time ago, about hundreds of years, about 2000 years ago, people used to communicate by with the smoke signals. If something happened, you burn some wood and then you let the smoke signal go up. A person at some other distance can view the smoke signal and then say that, oh, something must have happened. This kind of a visual communication via smoke signal or by lighting up torches and then relaying the information was known. People used light for communication, but of course, the thing with those communication systems are that they are extremely low data rate, and they are susceptible to lot of problems because of the channel and weather conditions, and the distance with which you could perform this communication was limited. So, you light up a torch, it can go only so far, before that other person cannot see anything. So, these were characterized by very low data rates, they were characterized by short distances and a high amount of loss because of the weather conditions. Things started improving, and people in the 1960s came up with the idea of using optical waveguides, or they came up with the idea of using glass fibers. These fibers, which are very thin, are supposed to guide light using the mechanism of total internal reflection. So, this was proposed. However, low loss optical fibers were not available because the fabricated optical fibers had significant significant impurities, mainly from the water content in the fabrication. Then people refined the fabrication process, and finally what came out was a low loss optical fiber. Throughout this 10-year journey where optical fibers were proposed, but their losses were reduced in the year 1970, there were a couple of people who were championing the cause of optical communications, and one of this person was Charles Cow, who jointly won Nobel Prize for championing the cause and for popularizing the cause of optical fiber communications. He won a Nobel Prize in the year 2009. Today, however, low loss optical fibers are available, lasers are available, and then high data rate communication is enabled today. In addition to fibers, lasers, detectors, all these improvements, today there is a significant communication technology enabler in the form of coherent detection plus digital signal processing. Coherent detection was used in the first 3 generations of optical networks. However, there coherent detection was very difficult to scale up for higher bit rates. Today, coherent detection is combined with digital signal processing, which makes the data rates go at 100 Gbps, and now the next technology at 400 Gbps and beyond. If you look at how a typical optical fiber communication system looks, this is how it would look. Of course, I have not put all the components that are necessary over here. We have a data that is almost always digital. So, data is almost always digital. This data is mapped to an appropriate, by using an appropriate mapping technology. We will talk about what this mapping is, what this modulation methodology is later. In this case, this is called as a QPSK modulator. From this QPSK modulator, you take the mapped data. This is still in the baseband or in the digital domain. This is still the data that needs to be transmitted over the optical fiber. In order to transmit it over the optical fiber, you need to modulate this data onto a laser. Laser is the optical source, optical carrier. So, you modulate the laser and then transmit it over the fiber. You can choose to compensate for certain fiber impairments inside the link itself. This is known as inline dispersion compensation. Do not worry if you do not understand dispersion compensation, we will talk about it later. So, this is the standard single mode fiber whose losses are pretty low, and this will work in the wavelength range of 1550 nanometer. So, this current optical communication technology works in the range of 1550 nanometer, and these GS and GD are the optical amplifiers. These are used to overcome whatever the losses that are there in the channel. Okay. So, you will have multiple such what is called as a span. So, each span consisting of a single mode optical fiber and an amplifier. So, you have multiple such spans forming together the channel. At the receiver, you have a local oscillator which will mix with the incoming signal and then produce in phase and quadrature components. These in phase and quadrature components are analog signals, or these are the currents or voltages in the electrical domain. They will, which are continuous, but they will be sampled using very high speed analog to digital converters. Once you have sampled, you combine the digital samples and perform the rest of the signal processing. It could be phase estimation, it could be carrier frequency offset estimation, it could be anything else. You perform all this signal processing, eventually you try to recover the data. Of course, you will not always be able to recover the data, because lot of things can go wrong in this communication system, and one of the objectives of optical fiber communication system, the design objective is to minimize the error between what you are sending and what you are receiving. We will quantify more stringent error criteria in the next module. Okay. So, the key technologies that are driving optical fiber communication today are spectrally efficient modulation. You want to modulate your data onto the carrier in such a way as to minimize the total occupied bandwidth. Okay. So, for a given bandwidth, you want to squeeze in as much as data as possible. Then you also have to do some pre-processing at the transmitter side by performing some error correction. This is called as forward error correction. This is in anticipation of things that can go wrong in the channel. You also perform digital signal processing at the end, and then you also need to perform performance monitoring, or you need to actively monitor the performance of various blocks in this optical communication system, so as to consistently deliver high data rates. If you look at how optical fiber communication evolved, at the beginning you had in the 1970s the first generation optical fibers. They were working in the 800 nanometer regime. The data rates were pretty small, and the distance over which you could communicate was also small. SMF was introduced in 83. At the same time, DFB laser was also introduced. Of course, before that the lasers that were used were Fabry-Perot cavity lasers. We will talk about them later. And once SMF was introduced and the wavelength was pushed to 1550 nanometer, the data rate became 2.5 Gbps. That was the third generation optical networks. The first generation was working with 800 nanometer and multi-mode fibers. They were not very fast, or they did not have pretty high data rate. The data rate were in some 40 to 45 megabits per second. Later, in the second generation optical communication systems, the operating wavelength was moved to 1300 nanometers, because that happens to be a smaller attenuation compared to 800 nanometers. However, this smaller attenuation, actually this smaller attenuation also has zero dispersion. The single mode optical fiber, the so called 652D optical fiber, has zero dispersion wavelength at 1300 nanometer, which means that you do not have to worry about dispersion in that band, and that was made very attractive. Later, lot of other problems came up, and the attenuation was not as small as we thought. So, there was one more window which opened up at 1550 nanometer. That was a third generation optical communication systems, where the data rate, where the attenuation was at its lowest at 1550 nanometer. The attenuation is lowest, dispersion is not low, but it can be managed. Okay. So, this third generation data rate was 2.5 Gbps. The detection mechanism were all coherent detection. So, you had to have a local oscillator, and you had to control the phase of the local oscillator very accurately with respect to the incoming optical signal. This was a very challenging task, but the advantage was that the sensitivity can be pushed up to 6 to 8 dB. Okay. So, up to third generation coherent detection systems were very widely used. Something very radical happened in the late 80s, where people discovered an optical amplifier that would take fiber that would be coupled with fiber at the input, and it would produce it would produce an output through the fiber that could be coupled at the output. And the amplifier itself was made of a fiber, which could be easily pumped by having one more optical element at the input called a pump diode laser or a pump diode, okay, pump laser. Now, this amplifier is called as erbium doped amplifier. Its structure is very similar to the single mode fiber. However, this single mode fiber, when you dope it with this erbium ions, will allow you to amplify optical signals. The best part of this optical amplifier, that is the erbium doped optical amplifier, was that you did not have to convert your input optical signals into electrical signals and then amplify. This was an all optical amplifier. You have multiple channels coming in, and all these channels could be amplified simultaneously by using the erbium doped fiber amplifier. So, you could use this erbium doped fiber amplifier to amplify optically all the signals. That also led to the concept of WDM systems, that is, instead of sending only one carrier in the optical fiber communication, you now break up the available spectrum into multiple channels. You modulate each channel with data coming in from different sources. You put all of them together into an optical multiplexer and then send it over the fiber. If the fiber is getting, if the data is getting lossy because because of the fiber losses, you simply put an optical amplifier in the form of an EDFA, amplify all the channels simultaneously and then transmit over the next or the remaining part of the fiber network. So, this advantage of having WDM systems and later to dense WDM systems or DWDM systems meant that you could pack in lot many channels, and each channel contributing data rates of at least 2.5 to 10 Gbps of the data rate. So, you have an aggregate data rate which was already going up. This WDM technology was the one which made possible internet connections, because it delivered very high data rates to the users who are connected very far away distances. Of course, from there you see that the data rates have been pushed up, increasing and increasing, and this is a figure which is quite old now. This is up to the year 2010, but you can see that already at 2010 you have systems demonstrations such as 112 gigabits per second, and there are 112 channels in the aggregate. So, the total data rate is 112 by 112. The experimental reach already came in, the system operation already came with 100 G, that is now going to be standardized very shortly. So, in between you had 2.5, 10 Gbps, from 10 it went to an intermediate 40 Gbps stage, from 40 we are now at 100 G. So, current technology is at 100 gigabits per second technology. So, we will see what makes the current technology and what enables the current technology as we go along with the course. Now, one thing which I would like to emphasize is that optical communications earlier were quite simple. If you take a standard textbook on optical communications which was published in the year 90s or 80s, you would see that modulation simply meant changing the laser current according to the signal that you want to send, and detection simply meant you put a receiver photo detector and then follow it up with a receiver amplifier. So, this is all your receiver consisted of, a detector and an amplifier. So, in a way the communication system was very simple. You had a simple transmitter, you had a simple structure for receiver. However, with this the current trends in optical communications which show that high data rates can be achieved, what they have done is that in order to get these high data rates per channel and in order to efficiently utilize the spectrum and to lower the cost per bit for the consumer, we have lost that simplicity. The modulator structure is now complicated, the receiver structure is even more complicated, and the enabling technology all have to go in order to ensure that higher data rates per channel are achieved. And of course, the advantage is that if you do this higher data rates per channel, then you are efficiently utilizing the spectrum, and so as a consumer there will be less amount of cost per bit that you consume or that you transmit over the network. So, higher infrastructure costs go for telecom companies, which they will then recover by appropriately pricing their strategies. Okay. So, the point I wanted to make was we have increased the data rate at the cost of simpler transmitters and receivers. To get back to what communication means, communication is a very old concept. Even now I am communicating, of course, this is a one-way communication because I am talking and you are listening, and hopefully my ideas which I have been speaking for the last 20-30 minutes is going into you. So, this is one kind of communication which requires a person who is communicating, a medium which is internet in this particular lecture series, and a listener who will listen and interpret what the sender is saying. So, you have a sender, you have a channel and a receiver. Of course, the receiver can also send something back, not at the same time. So, you have these two parties which can communicate over the channel in a bilateral way. So, sender can become a receiver, receiver can become a sender after some time. The idea for the sender would be to send messages as fast as possible and make as many less errors as possible. So, the communication channels must ensure the communication channel which separates the sender and the receiver must ensure that messages are being delivered faster and they are being delivered with almost no errors. If you look at a typical communication system, there are certain layers in which the communication system is organized in order to facilitate the entire communication process. At the top you have an application layer. For example, if I am typing an email to be sent out to my friend who does not reside in India, but resides say in United States, I type something on my computer and then say put it into an email program and then say hit button. So, I press the send button and this message is then transmitted to my friend. This layer which completely shields me away as to what is happening inside. How is it possible that I if I press a button here, the message is delivered almost without any delay to my friend? That entire mechanism is invisible to me, and this mechanism in which I am only concerned with how to utilize these applications is called as the application layer. So, on the application layer we are completely oblivious to the mechanism of communication. So, if you want to understand how communication is happening, you need to go down one level below. This is sometimes called as the network layer. So, what happens is that the message that needs to be communicated to the receiver must be tagged appropriately. Think of posting a letter. When you post a letter without mentioning the address, it cannot go anywhere. It can go any place it wants, but it does not always go to the receiver. So, in order to make it go to the intended receiver, you need to put in the address, router, all this information needs to be put in. So, the email that I entered, which is just a stroke of keys from the keyboard, will be converted into bits, because most communication systems are digital. So, they will convert it into bits, and these bits are tagged with addresses in order to make it go to the intended recipient. Okay. Of course, this again shields the exact way in which this bit transfer is occurring, right. So, one can take these bits and then carry physically over to the receiver, but that is not what we normally mean by communication system. So, if you go one level below, you will see that these bits actually are input to a device called as transmitter, which will then prepare this information which it has received into a form that is suitable for transmission over the channel. And based on what address and router information has been given, this waveforms which are suitable for the channel and they are carrying the information that needs to go from sender to receiver will be switched, routed and placed appropriately. At the receiver side, you have the physical layer receiver, which will receive the information from the channel and convert it into a form that is suitable for the receiver to read. If you receive ones and zeros, or if you receive currents and voltages, you will not be able to understand what is being transmitted. So, these voltages and currents have to be converted in the form that you can understand, and the form that you can understand is perhaps the language that we are speaking right now. So, this entire thing has to be performed at the physical layer. For someone who is sitting at the network layer, it seems that some bits are going in and some bits are coming out with occasional errors. So, this entire physical layer will look like a bit pipe. Okay. So, bits go in, bits come out. So, this sometimes there would be errors, but this bit pipe encapsulates whatever the functions that are necessary to convert bits, which are abstract entities, into actual voltages or currents or light waves, which can then be transmitted over the channel. Now, as I mentioned, much of communication happens today by digital means. There are very few analog links that are available. Even the analog communication systems such as AM and FM use analog only at the front end and at the back end. The remaining ends are all digital. Okay. So, if you go to an AM station or a FM station, only at the front end everything is analog, and the transmitting end where the waveforms are going as AM or FM. But once you have come to the actual circuits after the initial front end, all the remaining circuits are all there in the digital domain. So, why is it that everything has gone digital? There are several reasons why it is so. one of the important reasons is that digital signals are immune to noise, because they can be regenerated and this information can be repeated. So, this regeneration and repeatability, which are excellent for digital communications compared to analog communications, makes it very attractive for us to work with digital communication systems. And there are various blocks that one can use when you are operating things digitally, and they can be purchased at very low cost because they have been nicely integrated by the VLSI technology. As I said, this regeneration repeatability comes because digital signals have a greater immunity to noise. The channel impairments can be easily we can easily undo the channel impairments using digital signal processing. You can use all kinds of DSP algorithms, very sophisticated, and these algorithms allow you to overcome the channel impairments. And switching and routing operations are very easy with digital communication systems. They are very difficult with analog communication systems. They are very easy. You can tag headers, you can tag footers, you can tag whatever that you want, and in order to switch and route the appropriate bits or packets. If you look at elements of digital communication system, you will see a codec at the input side, which consists of the bits. Bits are coded in order to reduce the redundancy amongst them, and then these bits are then further encoded in order to deal with the channel impairments. So, this is called as channel coding, and they have to be of course converted into a form that is suitable for transmission, that can be performed by a modulation block. And normally this block that you see after modulation has data in its base band, as we would call. This baseband data needs to be converted into passband using an upconversion process. For example, this could be an electrical signal, but my channel would be optical channel. So, I need to convert these electrical signals onto optical signals. So, I can do that by upconversion process. The channel will then carry the appropriate waveform. At the receiver side, you demodulate and recover back your baseband signal, which you then down convert and recover back your electrical signal. You then demodulate, you perform channel decoding, source decoding, you also perform some signal processing operations to recover your bits. Okay. As I said, this is just an optical fiber communication that would exist today. This could be an example of 100 gigabits per second single channel optical link. Okay. It is not an optical network, it is a single channel optical link. If you look at what is required to modulate this data, you will see that you have a laser diode. Laser diode normally emits light, which is continuous wave, that is, it is like an oscillator which is oscillating with a particular waveform. However, if you want to modify the characteristics of this waveform, you need to modulate its amplitude, frequency, phase, or any of these combinations. Normally, we modulate the amplitude and phase. This is called as quadrature amplitude modulation. If you simply choose to modulate the amplitude or equivalently intensity, this is called as intensity modulation. What you would like to do? Well, I know that this is the waveform which I want to send, let us say, and I know this is the laser light output as a function of the current. So, imagine this as a diode, and this electrical signal is driving the current. So, if the current increases, the light output power will increase. If the current here at the input decreases, the light power decreases. So, whatever the variations that are happening at the electrical side will be carried over to the optical side. This is called as direct modulation of the laser, and this was the technology that was used in the first 4 generations of optical communications for data rates up to 10 Gbps. Now, instead of using only intensity modulation, if you want to pack in more and more data onto the same bandwidth, you want to use modulators which can perform phase modulation. You want to modulate not only amplitude, you want to modulate phase as well, so that you can put in more information. And in some sense, we will see later, optical phase modulation is one of the easiest things to perform rather than optical amplitude modulation. Okay. So, phase modulator is the building block including an optical modulator. So, all external modulators include phase modulator as one of its units. You can play around with the phase modulators to come up with amplitude modulator structures as well. In today's technology, Y or Z cut lithium niobate crystals are the substrates that are used for optical phase modulation. Okay. We will study more about how phase modulation occurs and what is the physics behind this phase modulation as we go ahead with the other parts of the course. You can combine phase modulators, put them together to form a Mach-Zehnder modulator, which consists of 2 phase modulators. You can see one phase modulator at the top, you can see one more phase modulator at the bottom. You can drive it with 2 signals. This is called as a dual drive Mach-Zehnder modulator, and the transfer characteristic of this which you can see here shows that it is a nonlinear transfer characteristic, but if you want to operate in the linear region, that is if you want to send in analog signals, you would like to operate this in the linear region, which is called as the quad point operation. You put your bias point at the dot that is shown here. If you want to operate digitally, you operate either at the minima or at the maxima of the signal and then drive from minima to the maxima. Okay. So, this Mach Zehnder modulator allows you to perform analog modulation as well as digital modulation. It also allows you to create pulses out of continuous wave light, as we will see later. You can put together two such Mach Zehnder modulators and one phase modulator in order to perform what is called as quadrature amplitude modulation. With quadrature amplitude modulation, you are able to perform both amplitude as well as phase modulation combined together. Okay. As I said, you can use Mach Zehnder modulators for pulse carvers. Various duty cycles or various area under the pulses can be achieved. This is a 33% duty cycle, this is 50% duty cycle, and this is 67% duty cycle for the waveforms, wherein you send in a continuous wave signal and out comes your pulsed waveform. Okay. We will see how you can perform all these pulsed waveforms, or you can generate these pulses later as we go to the course. As I said, you can modulate amplitude. If you simply choose to modulate the amplitude of the carrier, this is equivalent of intensity modulation. You can either turn on the light source or turn off the light source. When you turn off the light source, the amplitude of the light going is 0. When you turn on the light, the amplitude could be something or the power could be something. We will normalize it and call this amplitude to be equal to 1. So, this is called as amplitude shift keying modulation. This is inherently a digital modulation. Your data comes in the forms of zeros and ones. To send a 0, you send nothing. To send a 1, you send some amount of light for a short duration. A spectrally efficient modulation would require you to modulate both amplitude and phase. This is an example of a star quadrature amplitude modulation. You can see that there are 16 states in this. So, there are 16 possible bit combinations that you can transmit. If, for example, you want to transmit the bit sequence 1111, then you transmit an amplitude of some R2. At the same time, you also have the phase of 90 degrees. So, this is the in phase axis, is the quadrature axis. We will come to that when we discuss modulation basics in the next few modules. Okay. So, this is an example of a transmitter. Now, when you come to a receiver, an ordinary PN junction can act like a receiver. Okay. However, if you want to make good quality receivers, then you have to do some additional things to the PN diode, and those additional things are in the form of the structure, in the form of doping concentration, in the form of the structure or the device itself. This entire thing we will discuss later. The device which responds by changing its electrical current to the incoming light is called as a photodiode, and this photodiode will allow you to convert optical variations into electrical variations. The fact about photodiode is that they are only sensitive to intensity. They do not really care what is the phase of the input signal. Okay. And as such, they can be used in what is called as incoherent detection. In this method of detection, which is also called as direct detection, you are only concerned with optical intensity. So, your data is coming in either as some light pulse or no light pulse or no light pulse, and you put in a detector. If there is no input, the detector will produce 0 ideally, and if there is some light pulse, the detector will produce a certain current, which will then be converted into a voltage and amplified. Okay. There is no requirement of controlling the phase, there is no requirement of controlling the polarization, everything is very simple. This has a very simple electrical and optical complexity. Of course, this is not suitable for demodulating or detecting phase modulated systems. So, in order to detect phase from the incoming signal, you have to use what is called as a coherent receiver. A coherent receiver is the one which mixes the incoming signal, which I have represented as ES, with the local oscillator signal ELO, and after mixing, you put them through the photodetectors, take the difference in the photocurrents and then amplify it. You will be able to recover both the in phase as well as quadrature components. Of course, when you recover the in phase and quadrature components, you are also going to look at some noise in the receiver systems, and that noise will be part of your detected currents. The information that you are transmitting resides in the amplitude A of t and in the phase phi of t. Both can be recovered by this coherent receiver. You can do one step better than a coherent receiver. You can split the incoming signal into two parts, because we will later learn that fibers can support two polarizations, and it is criminally wasteful to just waste one polarization. So, we normally modulate on both the polarization degrees of freedom. You can recover this entire polarization of the incoming signal by splitting the input signal into its respective orthogonally polarized components, mix them with the local oscillator component, which is again split into two orthogonally polarized components, and perform an IQ demodulation at the two ends, and then combine appropriately to obtain the full polarized electric field. So, you have gotten full information about whatever that has been transmitted. As a final point, I would like to tell you that this process by which you obtain the currents, the in phase and quadrature currents, are not the end of optical communication systems. In fact, for high data rate systems, that is just the beginning. From here, you perform low pass filtering in order to remove some noise and other components that are not of interest. Then you convert this continuous time signal into discrete time signal by sampling them through a high speed analog to digital converter. Once these samples are available, you can then perform operations such as timing recovery, adaptive equalization. You can perform phase estimation in order to obtain the carrier, in order to recover the carrier phase. You can do all this by using highly sophisticated digital signal processing algorithms. Okay. The next and the last part which I would like to show to you now is an optical fiber. An optical fiber is the guiding layer which allows you to take data from one point to another point. In its simplest structure, an optical fiber consists of a cylindrical core and a cylindrical cladding that is surrounding. The core has a higher refractive index, the cladding has a lower refractive index, and light in a very simplified analysis can be considered as being guided by total internal reflection. What are the good things about this optical fiber? The optical fiber has low loss and large bandwidth. However, two impairments which are common to optical communication systems because of the fiber are dispersion and nonlinearity. So, we will spend some time in discussing dispersion and nonlinear compensation schemes. If you look at the structure of a single mode optical fiber, the core diameter is around 8 micron or the core radius is around 4 micron. The cladding is standardized to 125 micron. Covering the cladding is a buffer at 250 micron, and finally a jacket at around 400 microns. Okay. So, these are some of the modes in the optical fiber. When you send light, light arranges itself in this fashion. The intensity here is at the center is maximum, the intensity keeps dropping as you move away from the center in this mode. This is the fundamental mode, this is called as LP01 mode. Then you have higher order modes, which are all the different patterns in which electric fields can be found inside an optical fiber. We will discuss fiber modes and tell you how to obtain these beautiful colored pictures later in the course. This is the fundamental mode. As I said, the core has its larger intensity and the intensity of the light starts to drop off as you move away from the core. The effective content of the energy inside the core is measured by what is called as the mode field diameter, which is the distance over which the light is concentrated by. Light is higher than 1 by E. So, it is around 90% of the power is concentrated inside this mode field diameter of the fiber. So, earlier transmission of optical fiber happened, the first generation happened at 800 nanometer because the loss there was at its lowest. Then came 1300 nanometer window, which is this one, and this is the 1300 nanometer window, and finally you have the window at 1550 nanometer, which is the lowest loss, and the typical loss in installed fibers is around 0.2 dB per kilometer. As I said, dispersion is a major impairment in the fibers. There are two kinds of dispersion. One is called as material dispersion. This occurs because of the silica molecules, and then there is waveguide dispersion, which is because of the cylindrical construction of the optical fiber. The total dispersion is the sum of these two, and for standard single mode fibers, this zero dispersion occurs at 1300 nanometers. However, this dispersion can be moved, the zero dispersion window can be moved to 1550 nanometer by appropriately tailoring the material dispersion. What is the effect of dispersion? The effect of dispersion is to basically broaden the pulse. So, as the pulse starts to spread, as the pulse starts to propagate through the fiber, it starts to broaden. Why should we care about that? Well, you are not going to send only one pulse, you will be sending one pulse and immediately you will be sending one more pulse with a certain distance between the two. So, if the first pulse spreads out and then occupies the slot for the second pulse, then the second pulse and the first pulse will talk to each other, and then you will not be able to recover which pulse corresponds to what. So, you will actually have what is called as inter-symbol interference. One symbol is interfering with the other symbol. And finally, optical fibers at low launch powers, low optical powers are very good linear channels. However, this linearity is lost as soon as you start pumping in larger optical power. Because an optical fiber itself is a very small structure, the core diameter is 4 micron, the power density, even if you put in just 1 milliwatt, the power density inside an optical core is very high, and that will give rise to nonlinear effects. One of the major impairments of this nonlinear effect is to disturb the phase of the input or the transmitting signal. So, at the transmitter, if you have this constellation, we will talk about what constellation is in the next module. This constellation gets degraded as it propagates through the fiber, and you can almost make out nothing from this, but this can be restored by some good digital signal processing algorithms in order to, from the good digital signal processing algorithms to recover what you have been transmitting. So, this is an example of a 16 QAM phase estimation. Again, you can see that you can almost distinguish nothing here in the middle diagram, and then you can recover almost all of the symbols that you have transmitted after performing digital signal processing. In future, or it is almost already current, people are looking at multi-core fibers where there are multiple cores. Data can be introduced into each core. It is like multiple antennas at the input end and multiple receivers at the output end. You can also use a multi-mode fibers and launch light in the different modes of the fiber, okay, and you can combine them with appropriate digital signal processing algorithms to form what is called as SDM MIMO. SDM stands for space division multiplexing and MIMO stands for multiple input and multiple output. If you want to study optical communications, you have to understand 3 layers. One, at the functional level, you want to know what a functional block does, what does a modulator do, what does a laser do, what is its input characteristic, what is its output characteristic, what should I feed in to control this. Then you have to know how a laser is made, how a modulator is made, how a photodetector is made, what are the things that can go wrong when you make them. So, you want to assess the performance of these optical elements when they are placed in the appropriate optical communication links. So, we understand functional realization and performance assessment in this course by first focusing on the functional, then talking about the physical realization, and finally putting them together to assess the performance of these blocks. What background is required for taking this course and to extract the maximum benefit out of this course? I assume that you are familiar with analog and digital communication basics. I will review some fundamentals of digital communication and analog communication, but remember, this is just a review. I would appreciate it if you would read up on analog and digital communication fundamentals before listening to these lectures. I also assume that you have taken electromagnetics. You do not have to know optics. I will teach you whatever the optics that is necessary. Electromagnetics at the level of introducing you to Maxwell's equation is what I assume. So, I hope that you would brush up that part, and you should also know a little bit about signal systems and digital signal processing fundamentals. I will cover all these topics as and when they are required, but my coverage will be slightly rapid because my focus is not on this, my focus is on how they can be applied for optical communication systems. The course plan that I am following will be to first talk about optical fiber communication. We have already talked about that. Then I will talk about some digital communication fundamentals, some line coding, pulse shaping, which is common to both analog and digital communication systems. We will talk about optical transmitters, optical receivers, lasers, optical amplifiers, optical fibers and fiber modes. What are the WDM components like multiplexers, filters, arrayed waveguide gratings, fiber Bragg gratings, all those things we will talk. And finally, we will talk about DSP and optical communications. For most part of this, the textbook that I would be following is Optical Fiber Communications by Keyser. A 5th low cost edition is available in India, and there is another book which I would follow from time to time. I will let you know when I am following the textbook. It's Fiber Optic Communications by Shivakumar and Dean. This unfortunately to my knowledge does not come in a low cost paperback edition. So, with this I close this module, and I look forward to discussing some fundamentals of analog and digital communications, and then moving on to the functional description of the optical transmitter blocks and how optical communication can be used to perform analog and digital modulation. Thank you.